All right, here. Let's see what y'all did. All right, any questions on grabbing a calculator? All right, okay, good. If a bacteria population of 8 cells quadruples every 11 minutes, write a model of the form B of T. I chose B for bacteria. You could choose A for amount, or Y, equals A times B to the Tth power. That gives the bacteria population in T minutes. Okay, so here we go. B of T is, we need the initial amount. That's what A is, right? Or A sub O, if you want to call it that. What was it? 8. Good. 8 times, if something quadruples, what would be the scale factor? 4. So we'll put times 4 to the, and now if we just put to the Tth power, that's going to quadruple every single minute. We want it to be every 11 minutes. So what modification do we do to the exponent? Divide by 11. There you go. And so notice what that does. Every multiple of 11 now gives you another factor of 4. You plug in a 0, you get 4 to the 0, which is 1. You plug in an 11, you get 11 by 11 is 1, so that's one factor of 4. 22 divided by 11 is 2. That gives you your next factor of 4. So remember, it's just the base raised to the time divided by the amount of time it takes for that scale factor. Now, we better do something here off to the side. What units are we measuring T in? Minutes. So T in minutes. Even though it says it does that every T minutes, well, this one says to put it in terms of minutes. You would want to address that if it hadn't said that, because units are very, very important, and someone can use your model with the wrong units to get the wrong answer. What is B measured in for what it's worth? Yeah, cells or bacteria, whatever you want to call it. So those would be the units. Okay. Now, the whole purpose of writing a mathematical model is not just to write it and say, look what I made, right? Mathematical Model Appreciation Day. That's not today. We want to use it, right? We want to use it. The beauty of the donut is in the eating of the donut. We want to eat the equation. That analogy. All right. So here, let's do some follow-up questiones. Part A, what is the population after 2 hours? So remember, there's really 2 ways to use these formulas. I either give you a T value and you plug and chug, or I give you a B value and you set it equal to and graph it and solve it. Is 2 hours a T value or a B value? It's a T value. So do I just plug in a 2 for T up here? No. Are units important? Yeah. If we're measuring T in minutes, then 2 hours is how many minutes? 120 minutes. So units are very important. So when we quiz on Wednesday, you'll have a practice free response quiz on Wednesday, or we take the ultimate test on Thursday, notation on the free response is important. So here's what you're going to put. You're going to put B of 120, okay, or A of 120, whatever the equation's name is, of 120. That communicates that you're plugging in a 120 for T. Now, if you just type this into the home screen, 8 times 4 raised to the 120 divided by 11, that's fine. But when you have an equation and you're going to be asked multiple questions about it, you want to get in the habit of typing it into Y1. So let's go ahead and do that. Here's where your calculator comes in. Turn it on. Why is mine not on? There it is. Boom. You go to Y equals and you type it in. So that's 8 times 4 caret. And then you could just put X divided by 11 or 1/11 times X. That's probably the quickest way to do it. Remember, we use X instead of T. So you make sure, double check that it's in there correctly, and now we go to the home screen. We don't graph it. If it's a plug and chug variety where I give you the independent variable, you go to the home screen and you recall it from Y1. Remember to do that, you hit alpha trace. Yeah. Now when you hit the green alpha button, if you're not sure where it is, notice there's a menu at the bottom. You could just toggle left and right to figure out where it is. So there it is, number 1. And just like we have on our paper in function notation, open parentheses, 120, close parentheses, and you hit enter. And then you write it down, 2958129.3.82. Okay? And then if you want, you can come back and put commas. It's not entirely required, but that kind of helps you read the numbers. So that's 29 million, and then what are the units at the end? Is that minutes or cells? Cells, bacteria cells. Good. So always put units on your final numeric answers. All right, questions on that one? All right, so the other way we can use the model is if I give you a dependent variable, an output. That's like B. After how many minutes will the population reach 3,000? 3,000 is now a B value. Now, when we learn logs, you're going to actually set this part of the equation, 8 times 4 to the t divided by 11. You're going to set it equal to the number and solve it algebraically. But that's not how we're doing it today, okay, or on Thursday on the test. So all you have to show me is that B of t equals 3,000. That's the quicker way to do it because that's the name of the function. B of t equals 3,000. So that tells me now what equation you're solving. Now you go back to the calculator, and in y1 we still have our function b of t, so in y2 or wherever you want, we'll type in 3,000. Now if you just hit graph, or zoom 6 I should say, you're going to be like, cool. You're probably going to raise your hand on the test and say, I don't see anything. I'm going to be like, you shouldn't in that window, okay? So let's think about what we're doing. We're measuring time on the x-axis. 0 could be a lower bound, but I like to put -1 because then it still shows the y-axis. X max is the one that we're going to have to play around with. We're not sure what that's going to be. How many minutes do you want to go by? Well, we know 120 was way too big. That got to 29 million. So what if I just went to like, I don't know, let's give it an hour, 60 minutes. That one we'll come back and play with if it doesn't work. Y min, again, we're measuring bacteria. We can't have negative bacteria. So if you want to put 0, that's fine. -1 allows you to see the x-axis, which isn't bad. Now the Y max should not be guessing because we know we want it to at least include 3,000, yes? So we need to pick a value that's bigger than 3,000 because we don't want it to be at the very top of the screen. 3,001? I'm going to go to 3,500. You go ahead and do 3,001 if you want. I'm going to put a little bit more buffer space up there, or even 4,000. Now we're going to hit graph. It intersects. If I didn't see it intersect, like if I only saw this much of it, I would change my x max. If I went too far and I saw it like coming up here, I would trim down my x max. So there it is, and notice we have enough space up above. So now how do we find that point of intersection? Do we go to the table? No, we don't go to the table. We go to second trace now, not alpha trace, but second trace and number 5. So remember that if there's only 2 curves shown and there's only 1 point of intersection, you could just find the enter button and hit enter, 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 just like Emory just did, right? First curve, second curve, point of intersection. And there it is, 47 point, how many decimals do we report? 3 decimals, which is 029. Yeah. So underneath here, we put t equals, underneath that, we put t equals, and then 47.029. And that would be the same answer rounded or truncated. And then what would the units be? Cells or minutes? That's a time value. Yeah, it's going to be in minutes. Minutes. Okay? So if you forget units or you put the wrong units, like if you put cars there, that would be wrong. Okay? Also, if you're wrong in the third decimal, it's going to be incorrect. So that's it. You write the model, and then you use it to predict one of 2 ways. You either are given the input, that's plug and chug, that's that notation, or I give you the y value, and there's 2 lines you set it equal to, and then underneath there, t equals with units. That's it. If you can handle that, you pretty much have the basic idea for all these exponential growth and decay functions. Any comments or questions on that one? Okay, so I think we're sufficiently warm. Let's jump down to example 7 now. It should be relatively easy in light of your warm-up. Because all we're doing on example 7 is we are writing the equations, okay? So it says determine the exponential function of the form y equals a times b to the tth power. So I'm giving you the form that satisfies the following conditions. Define the units that we're going to use for t. That's kind of important. All right, so if we have an initial value of 7 and the quantity, whatever it is, increases at a rate of 32% per day. Is 32% the growth rate or the growth factor? Yeah, that's the growth rate. And we know it's growth because it says increasing. So the growth factor, let's see, y equals 7 is the initial value. What would be the growth factor? In other words, what would be the base? Would it be 0.32? No, good. If you put 0.32, that's actually less than 1. That would be decay. Yeah, so remember, if you know what little r is, the growth rate, you could use like little g, little r. The growth rate is 0.32 plus what? 1. Or as we wrote at the beginning of the section, 1 plus 0.32. Right? Let's scroll up there and remember that. It was in the box. It's either 1 plus little r or 1 minus little r. The 1 represents 100%, right? So everything we had before, 100% plus an additional amount. So if you always think about the reasonableness of your answer before you walk away, you can catch careless mistakes. So I'm just going to call that 1.32, and then it increases at 32% per day. So what would the exponent be? T, right? Divided by 1 day or just T? But we better put T in what units? Days, right? If you don't put T in days, someone would maybe think that T is in hours, right? What if we wanted to do it in hours? T in hours. Could we use the same model and adjust it? Yeah. Would the 7 still be the same? Yep. Would the base or the rate still be the same? I'm sorry, the factor, not the rate. Yeah. What would the exponent be now? T over 24. Good. T over 24. So units are very, very important. And if you don't believe me, just ask NASA. Anyone heard of NASA? Yeah. There's a rover now on Mars that's walking around all day saying, cool, man. But he's the second version of the Mars rover, because in the initial Mars rover, when they were trying to land it on the surface of Mars, this was several years ago, they were communicating between Houston, which was command center, and Cape Kennedy, Cape Canaveral, which was the launch center. And they were controlling it, in Florida and getting the coordinates from Houston. Did y'all hear the story? What happened? Huh? No, the dust didn't cover the panel. Well, I guess you could say the dust covered the panel. What happened is it came in too hot, and it literally crashed into the surface of Mars and obliterated. Okay? And the reason is they were using different units. I kid you not, NASA. They were using different units back and forth between Florida and Texas, Houston and Cape Canaveral, and they were just using the magnitudes. They weren't putting units at the end, so they didn't know. Like one was using scientific units and the others were using standard units. And then, oops, there went the Mars rover. It was just a few bucks, right? Yeah, several hundreds of millions of dollars. Oops, oopsie. Yeah, I was using days, they were using hours, whatever, okay? So units are super, super important. Let's try this one. What if I wanted to measure in years? Oh, boy. Would it still be Y? Yeah. Would it still be 7? Yeah. Would it still be 1.32? Yeah. What would the exponent be? T over 365? No. Right. 1 day is equal to 1/365.25-ish. We'll just use 365 of a year. So remember, we did this on Thursday or Friday. When you do T divided by, it's T divided by a fraction. That just looks yucky, yucky, gross, gross. So what can we do to make it look more purty? 365T. Yeah, 1.32 times 365T. And we'll just put T in years. So if you're ever using units that are bigger than the obvious ones, you're going to have a horizontal compression. It's going to be a number times T instead of a horizontal stretch. If you go with smaller or bigger, I'm sorry. Okay, part B. Go ahead and do it yourself. Give you a minute or two. If you've already done that, move on to C and D. We'll catch up with you. Your base here is 1.4. Is that growth or decay? Should be decreasing, right? Yeah. What's the base? What's the base? Remember, the base is also the factor, right? So this would be decay factor, and I'm giving you the decay rate. All right, so let's say this is a multiple choice question on the test on Thursday. Here's one of the answer choices. Y equals 427 times it's decreasing by 0.427. Now notice that is a percent already. Yeah? That's a percent. So if I want it as a decimal, I'm going to have to move it 2 units still further to the left. So that would be 0.00427 as a decimal. 0.00427 to the, it's per year, so I could say T divided by 1, or just let it be T and say that T is in years. Is that model growth or decay? It's decay. The base is less than 1. Is that the right model for this situation? No, it is not. Okay, good. So that would be an answer choice on the test for sure, but it wouldn't be the right one. So remember, what we have to do is, in this case, subtract from 100. So you either do 100% minus 0.427, or if you want to do it in decimal form, let's do it in percent form, and then we'll convert it, okay? It's probably a little bit easier. So we're going to have 100%, and then we're going to subtract. We've got to line up the decimals, 0.427. So let me get that percent symbol to go away, and I'll have 0, 0, 0. So there's going to be a lot of borrowing going on here, right? That becomes a 9, 9, 9, 9, and then a 10. Good old-fashioned subtraction. So we get a 3, we get a 7, we get a 5, point, and then 99. So if we're only losing 0.427%, we're essentially retaining 99.573%. And now you could put that as a decimal, and your base becomes, this was wrong, you get y equals 427 times 0.99573 to the tth power, where t is in years. Okay? Y'all got that? You always have to subtract from 100 or add to 100. You want to work with percentages and then convert them, you have fewer zeros to work with. Yeah. Okay, real quickly, let's do the same one, but let's measure it not in years, but let's just measure it in days. What would it be if we measure it in days? How many days in a year again? 365. Here's 2 answer choices possibly from the test. We'll call it answer choice A and B. One divides by 365, one multiplies by 365. Which one's correct here? A. Good. Okay? Because if it's per year, just off to the side, 1 year is not 1/365th of a day, but 365 days. Okay, so those are the same number. All right, so you divide by the same number. If that number ends up being a fraction, then of course, say, change, flip. Good. All right, so that's if I give you the percentage. Hi, welcome. Part C and D, this one should be a little bit faster because of what we just did in the warm-up. So let's go ahead and do it. The initial value is 18, so we put 18. Again, if the base, if it's quadrupling, that's the factor, growth factor. What's the base going to be? Also 4. And then the easiest version of the exponent would be t what? Divide by 13. Yeah. And we'll just say t is in minutes. Good. There we go. Pretty easy. I'm not going to do another version of that. 13 minutes is not a really nice number. Okay, part D. Go ahead and do that one. That one has interesting units and numbers. Zoom out. You forgot your exponent, right? Yeah. Oh, you're trying to figure it out. Oh, okay. Yeah. I mean, remember, you could choose whatever unit you want here. I'm giving you kind of a wacky unit, but whatever unit you choose, then it's going to affect your exponent, and you're going to have to say off to the side what unit you are electing to use. All right, so let's do this one together. Y equals, the initial value is 26.3. Anyone recognize the significance of that number? It has a decimal in it. Good. Anyone, was anyone in New York yesterday? No? Anyone hear about what happened in New York yesterday? Beautiful day in New York yesterday. There's always money involved in everything, yeah. No, this involved more like sneakers and runners. The New York Marathon was yesterday. Yeah, the New York Marathon was yesterday. The guy that won it in 2 hours, 5 minutes, and 59 seconds. That's super fast. He was running like 4.5-minute miles for 26.3 miles. That's the current length of a marathon in miles, 26.3. The world record's like 2:03. The 2-hour threshold for the marathon is the new threshold. It's like the new 4-minute mile. They're getting closer and closer to 2 hours. The female that won yesterday was 2 hours, 22 minutes, like 3 minutes ahead of the second place person. So they're flying. But why 0.3? Anyone know? Why not just 26 miles? The original marathon was when Phidippides ran as a messenger, right, in ancient Greece. And I think that was like 24.85 miles. So when they added it to the Olympics, they did it like 24.85. And then they adjusted it for a little while. It was like 25 miles and then 24.85. And then they established on 26 miles. But why the 0.3? In 1908 at the London Games, they added another 385 yards on to 26 miles just so that the runners could finish right in front of the British royalty box at the stadium, which was an extra 385 yards. So that's where the 0.3 comes from. It's convenient for the royal family for them to finish right there. Okay? So anyway, that's kind of interesting history. 26.3 miles. If it halves, what would be a good base? 1/2 or 0.5? I don't care which one you use. 0.5 is a terminating decimal, so feel free to use it. I prefer the 1/2. Just remember, if you write it as a fraction, put it in parentheses. And it's every 3 fortnights. So if I'm going to use units of fortnights, which we don't use very often anymore, it's going to be t divided by 3. And off to the side here, I'm going to say t is in fortnights. Well, how long is a fortnight? A 10-minute game? A fortnight is 2 weeks. A fortnight is 2 weeks. So if you don't want to use fortnight units, I don't blame you. So let's go ahead and do it in weeks, which makes more sense. So that would be y equals 26.3. I'll put it as 0.5 this time just to show the other version. What would the new exponent be? T divided by 6. Good. If 3 fortnights is the time, and every fortnight is 2 weeks. That's 3 times 2, that's 6. That's t divided by 6. Now t is in weeks. All right, what if we want to do t in years? Do that one. If this were like a multiple choice question or a free response, I would specify the units. Bless you. You have to have a little bit of cultural literacy to come in here, right? To know that there's usually about 4 weeks in a month. There's usually 7 days in a week. How many weeks are there in a year? There's 52 weeks in a year. So if that's every fortnight, 3 fortnights is having every 3 fortnights. That's every 2 weeks. Oh, there we go. 2 weeks is what fraction of a year? 2/52ths, right? It's 2/52ths, which is the same as 26. Yeah, there's 26 fortnights in a year. Okay, 26 fortnights. So that would be y equals 26.3 times 1/2 or 0.5 to the. Would it be t divided by 26? Good. It would be 26 times t. I'm going to skip that intermediate step. T divided by the quantity 1 over 26. Stay, change, flip. Woo! Good boy. Wouldn't that be cool if the dog did that? Stay, stay. Good boy. Change. And the dog becomes like a cat. And then flip. Good boy. All righty. Back to the topic. Any questions on that one? Okay. Let's shift gears here and talk about radioactive decay. We kind of mentioned it at the beginning of the lesson. We have the atomic, or we have the periodic table of elements, right? And there's a lot of elements on there, lots of them. I think they're discovering new ones every fortnight or so. Some of the elements are very stable. You can like hold them in your hand, right? In fact, I think I'm holding some right now in my hand. Kind of small. Some of them are not stable, right? Like they're round, so if you hold them in your hand, they might roll out. Is that what I mean by stable? No. They're radioactive. They're isotopes, which means they're kind of they're a little heavier or lighter than the stable versions. And if they're not stable, that means that they're radioactive. And you know who the first person to use radioactive terminology was? Famous woman, won 2 Nobel Prizes, Marie Curie. Yeah, gave her life, right? Died of radioactive poisoning. So radioactive just means that they're changing. They're emitting part of their mass. They're losing it. So we typically measure radioactive decay as half-lives. I mean, we can measure it in 4th lives or 3rd lives if we want, but the scientific community said 1/2 is a nice number, right? So that means we determine how long it takes in whatever units for a certain mass of some radioactive element or isotope to lose half of its mass. How long does that take? Okay, so let's look at one of my favorites, radium-225, an unstable isotope of radium. Now, if someone offered you radium of any type, would you take it? Yeah, but you got to be careful because radium in any state is radioactive. There's no stable version of radium like there is for oxygen or carbon-12, right? There is no stable radium. Now, 225 is an isotope. 225 is its atomic mass. It has a half-life of approximately 15 days. So just a smidgen more than a fortnight, right? It loses half of its mass every fortnight-ish. If we start with a 6-gram sample, don't ask me where we got that, and I probably should have given out permission slips before I had y'all handling these radioactive samples. My bad. If we start with 6 grams, I want to know, part A, how much of the original sample is left after 12 weeks or 6 fortnights, okay? All right, so what do? How do we start a problem like this? What's that? Yeah, y is kind of generic. I'm going to use A. Would you allow me to use A for amount? Thank you. A of t, reminding us it's a function of t. And now the initial amount could be 6, whether you call that A sub O or A if you use Y equals, that's fine. What would be our customary base, our factor, decay factor? 1/2 or 0.5. Good. And it's every 15 days. So if I want the easiest version, I just put T divided by 15. And then right here, I'm going to say T in days. We specify that. Otherwise, someone might mistake it for years or fortnights or helix. Ooh, you ever heard helix? Heleks. Yeah, it's about 3 seconds, right? There went another helix. Okay. So now that we have the model, we want to use it. Part A says how much is left after 12 weeks. Is 12 weeks a time value or an amount of weight? Yeah, it's time, 12 weeks. So we go A of 12 equals, right? No. If you do that, you should apply at NASA. All right. Because we're measuring in days, so you got to be very conscientious. We want 12 weeks. 12 weeks is equal to how many days? 84. Good. Because there's 7 weeks always. I'm sorry, 7 days always in a week. 7 times 12 is 84 days. So we'll put A of 84. Again, that's what you're going to show me. Now, you could just plug it in there and chug it, but we're going to put it into the calculator Medora. So go to your Y equals and flush. Get rid of that one. Type it in. 6 times 0.5 caret, that'll work, to the X divided by 15. Double check, triple check. Looking good? Yeah. Now, because it's a plug and chug variety, I'm not going to worry about graphing it. I'm just going to my home screen, second mode, get rid of that. And now how do we recall Y1? Alpha trace. We use the alpha trace and the second trace command quite a bit. There it is, number 1. Open, 84, close, enter. 0.123 or 0.124. Yeah. I'm going to put 123 for 2 reasons. I like to truncate, and if I put 124, that might mess people up who are trying to count. So what would the units be here? Grams, right? Grams. We started with a 6-gram sample. 84 days later, 12 weeks later, we're down to 0.123 grams. Okay, cool. Part B. How many days is it going to take for the original sample to decay all the way down to a single gram? How many days? Well, it should take fewer than 84 days, right? Because at 84, it's already less than 1. But the way we solve it, let's call this A, is now that I'm giving you the dependent variable, I'm giving you the 1 gram, all you have to do is show me A of T equals what? 1. You could put 6 times a half raised to the T divided by 15th equals 1. That would be fine too. But we're not going to do that now because that's what we would do if we were solving it algebraically. So right now, just use the name. It's a lot faster. A of T equals 1. If you don't show that on a quiz or a test, you're going to lose a check. Same thing if you don't show A of 84. All right? So now we go to the calculator, and we come down here to Y2, clear it out, type a 1. Now let's go to our window. -1 is still good. 60, if we let it go by the 60 days, I might try that. Okay, that's less than 84. And the Y min, I'll keep at 1, -1. Now the Y max, I know it has to include 1, right? So I'm going to go to 2, just to have space above. Here we go. I'm hoping it intersects. Hey, I got lucky. If I didn't see it intersect, I'm adjusting my X max only, okay, making it smaller or bigger. So from there, it's second trace, number 5, and then enter, enter. You don't need to scroll because there's only 1 point of intersection. There it is. Now, underneath A of T equals 1, you put T equals 38.774. 38.774. So that's how you do it. You don't put A of T equals 1 and then put equals 38.774. I've seen that a lot over the years. That is wrong for 2 reasons. First of all, T is that, not A of T. Okay, T is that, not A of T. And secondly, is 1 equal to 38.77? No. Nope. No. Now we better put units on the end. What are the units? Grams? Cars? Days. Yeah, cars. Nope. It's days. Good. All right, so that takes care of that question. So just like the warm-up, we wrote the model. I either gave you an input, gave you an output. You're getting the hang of it, right? Now, just a little side note here, radium-226, a slightly heavier version, is the most stable atomic weight, but it's still radioactive. It has a half-life, though, not of 15 days, but of 1,600 years. Wow. Okay, so relatively more stable, but still not very. Okay? Questions on that one? All right, letter 9. Letter 9. Suppose, when you read that, you kind of want to, like, rub your chin. Yeah, suppose. A radioactive sample loses 43% of its mass every 9,876 years. What percentage of the mass is going to be left after 2,000 years? Oh, boy. More than 43%, right? This is for a multiple choice question? Because it takes almost 10,000 years to get down to 43. So it should be about maybe a fifth. But how are we going to do a problem like this? We need to write a model, don't we? Okay, so let's do that. A of T equals, what's the initial amount? Yeah? A? Yeah? We could let it equal A, not A maybe because I'm using A for amount, but A sub O. It would be helpful to work with numbers, though. So y'all probably experienced this in a science class, I'm hoping. If you don't have an initial amount, you're just given percentages, it doesn't really matter what the initial amount is, okay? Because I'm asking you what percentage is going to be left, not how much is going to be left. So we can just work with any amounts. What's the most convenient amount to use for an initial value when you're working with per cents? 100. I would think 1 would be the second best. 100 would be the first best. Percent means out of 100. So let's go ahead and just let the initial value equal 100. Okay? What would the base be if it loses half of its, loses 43% of the mass? Good. It's not 0.43. Remember, that would be decay. So it's 100 minus 43, which is 57%. If we lose 43%, we retain 57%, and that's what we're measuring. We're measuring how much is left, 0.57. And it would be T to the what power? Or to the power of T what? Divided by, good, 9876. And then we'll put comma, T in years. There you go. There's a model. Beautiful. All right, now we can use it to answer part A. What percentage will be left after 2,000 years? Is 2,000 years an amount in samples, or is it amount of time? Time. So this is the plug and chug variety. So A of 2,000. And again, we're going to go to the calculator here. We're going to type that model into Y1, check it, double check it, make sure it's in there correctly, because we got a lot riding on it. We're going to be doing a lot of calculations with it. 100 times 0.57 to the T, or X, divided by 9876. Double check, triple check. It looks good, doesn't it? No, that doesn't look good at all. If you go with that, you're going to get some really wrong answers. All right, so make sure, double check, don't walk away. I hit the wrong button there. It was one below. There we go. Now it's X divided by 9876. That's looking better. Okay, I like that. So for the plug and chug variety, we just go back to the home screen, alpha trace, number 1, and then we type in a 200. We know that 200 works because we've checked the units. Is that right? No. What happened again? It's 2,000. Anyone ever make that mistake where you write down something that's wrong and then you keep looking at your work and now you're using wrong values? Yeah. So it's not difficult work, but you do have to be mindful and diligent. There it is, 89.24. Do we need that last zero, the third one? Absolutely we do. Good. Unless it's a terminating zero, it's part of the accuracy. So 240, and then the units are going to be, yeah, if we're talking about amount, it could be ounces or grams. We weren't given anything, so we'll just call it grams, right? But is that our final answer? No, we got to make sure we're answering the question being asked. It said what percentage is left. Well, if I started with 100 and now I have 89.240, what percentage is 89.240 of 100? Fantastic. So, some summative statement. Thus, consequently, ergo, therefore, whatever you want to write. So, 89.240% remains, and let's go ahead and make it a nice sentence, after 2,000 years. So now it doesn't really matter what the initial amount was. It could have been 5 grams, 5 ounces, 5 pounds, 25 kilos, whatever. We're going to be left with 89.240% of that original amount. All right, so that's part A. Label it. Part B. After how many years will the sample contain 22% of its original mass? After how many years? So now we're trying to find a T, so I need to plug in for A. Well, if I want to know when 22% is left, 22% of my initial amount, 100, is what? 22. Man, this is easy working with 100. So that's going to be my A of T. So now I say A of T equals 22. Go ahead and figure that one out on your own. Use your calculator. Again, we're in here until 10:36. I don't care if the bell rings right now or it didn't. Maybe they fixed it. I would think they would. This is where students start panicking on tests. They went to y equals. They have the function typed in y1. They put 22 in y2. And they hit graph, and they're like, I don't see anything. What can we do? Give up. Yeah. Just like I'm dropping this class, dropping out of school. Okay. No. You can either go and check your window, or look at this. Hit trace. If you hit trace, it's going to give you information, isn't it? Even though you don't see it, it's telling you that the y values are up there at what? 99. Oh, thanks for the hint, calculator. So let's come up here to y max and put it at like 110, whatever, something above 99. And now you're like, oh, okay. Man, it looks like 2 parallel lines now. These guys are supposed to intersect. Where do parallel lines intersect in the Euclidean plane? Never. Ruh-roh. We just need to give it some time, guys. Remember, 9876 is the half-life. Let's go out about 10,000 years. That's one half-life, okay? We only went out one half-life. That's not good. How many half-lives should we go out? Like 4? Okay, 9876 times 4. Are you allowed to type it in like that into X max? Sure. We're going out 4 half-lives. Let's see. Oh, that's 39,000. Okay. Oh, yeah. There you go. So you're thinking the whole time. Second trace, number 5, enter, enter, enter. T equals 26602.068. That's 26,602 and 68 thousandths. What? Unit? Years. Yeah. Now that is the answer. Okay? How long does it take to get 22% of its original mass? It's that. Okay, we're done for the day. The bell's going to ring in about 2 minutes. We're going to pick up tomorrow with a wonderful topic. Chernobyl, nuclear disaster. Wear your hazmat suits, people.